Okay, let's get started. Can people in back hear me? If you don't, you can sit in front. So today we are going to talk about some important distributions and concepts in probability theory. The first part will be some important distributions, not too many, just 5. In the second part, we are going to discuss whether there is a way to unify these distributions we discussed in the first part. And in the third part, we will have an overview of the conjugate pair. And lastly, we will discuss the estimation bias. So for the distributions, especially the 5 basic distributions, they are very fundamental in machine learning. When it comes to the graphic models, you can see that all the building blocks will be the 5 basic distributions. And we talked a little bit about the expectation and variance. The 5 distributions, as you know, are Bernoulli, beta, multinomial, Dirichlet, and Gaussian. So here is a general picture of how these distributions are used in machine learning. As you can see, many advanced machine learning models, such as Hayden-Markov model, the topic model, and the Dirichlet process, all of them are built on top of these distributions. So a quick overview of 2 important quantities with respect to a distribution, that is the expectation and variance. Expectation is the average value of a random variable under its probability distribution. If the random variable is discrete, you just do the summation. If the random variable is continuous, we use integral. This is what we learned in college. And for variance, it is a measure of how much variability there is in X around its mean value. So its definition is here. And on the rightmost part is an important equation, a property of the variance we are going to use a lot in the future. So here is a general picture of the distributions we are going to talk about. So given a random variable, according to whether its domain is discrete or continuous, we can partition them into 2 parts. For the discrete random variables, there are usually 2 cases. One is the event has 2 outcomes, such as you toss a die. It could be hand or tail. Another case would be the multiple outcomes. If you toss a coin, it has a hand or tail, 2 outcomes. If you toss a die, it has 6 outcomes, 1 to 6. So for the 2 outcome discrete variables, we will use Bernoulli distribution to model them. For the multiple outcome event, we are going to use multinomial distribution. If the random variable is continuous, as you know, we usually use Gaussian distribution to model it. So what about the other 2? Beta distribution, as far as I know, in machine learning, it is mostly used as a conjugate pair of the Bernoulli distribution. And for the Dirichlet distribution, it is usually used as a conjugate pair of the multinomial distribution. For conjugate pair, we are going to talk about later. And in Gaussian distribution, we know we have 2 parameters. One is the mean, and another is the variance. So if you want to put a prior over the mean parameter, we also usually use a Gaussian. So in some sense, Gaussian distribution is conjugate to itself. Okay, the first one is Bernoulli distribution. It is used to model binary variables. An event has two outcomes. We use 1 to denote that this event happens, and 0 to denote that this event does not happen. For example, in classification, in two-class classification problem, we use 1 to denote that the class label, let's say, suppose we have a picture. We want to classify it as whether it is tiger or not. So in this case, we are going to use Bernoulli distribution to model this variable. If x equals to 1, it means that this picture is a tiger. Otherwise, we use 0 to denote that this picture is not. The parameter of Bernoulli distribution is mu. The meaning of mu is that what is the probability of x equals to 1? In other words, what is the probability that an event happens? So if x equals to 0, the probability would be 1 minus mu, to ensure that the sum of the two quantities is 1. Here we talk about probability mass function, and if you recall, we have another term that is probability density function. Probability mass function and density function are both functions to characterize how likely an event happens. The difference is if the random variable is discrete, for example, in this case, we call this function as mass function. If the random variable x is continuous, we call this function as density function. So intuitively, we can write this mass function as px equals to mu if x equals to 1, and y minus mu if x equals to 0. But this form is not mathematically friendly. Means that you cannot deal with this function in analytical form. So usually we use another form, which shows on the right side, px equals to mu x 1 minus mu 1 minus x. If you plug in the value of x, say x equals to 1, you can say that if you plug x equal to 1 into this function, you will get mu, right? Because 1 minus x is 0, so this part here will be 1, and finally you get mu. If you plug x equals to 0 into it, it will be minus 1 minus mu. That is to say, these two definitions are the same, but the right part definition will be much more easy to handle in mathematics. The expectation of Bernoulli variable is mu, and its variance is mu multiplies 1 minus mu. So we can use this to remember that the definition of expectation is sum over all the possible outcomes I equals to 0 and 1, and xi pxi. This is the definition of expectation. So we plug in it. Would be 1 equals mu. By the definition of the variance, it is the expectation of x square here. Why we usually care about these two quantities, especially the expectation, because when you get a distribution, it is a function. A function is not nice to store and not nice to transmit and compute. So we usually use the expectation to characterize a random variable and all its distribution. This is a single quantity which is much easier to handle. So actually, when we get to the later part of this course, especially the graphical models, you can see that all we are dealing with is not the probability functions, but the expectations. So it's important to remember these two quantities, how to compute them with respect to a distribution. As I said before, for the discrete random variables, if it has two outcomes, we use Bernoulli distribution. So if the outcomes goes to k, where k is greater than 2, we use this multinomial distribution. So the multinomial is a generalization of the Bernoulli distribution. One trick here is suppose x is a multinomial random variable, which means that if it takes a value from 1 to k, usually we say x equals to 1, x equals to 2, down the way to x equals to k. But again, this kind of formulation is not easy to handle. So we have a trick here how to represent x. That is called 1 of k coding. 1 of k coding means that this coding vector is this x here is a vector. There is only one component in this vector equals to 1, and all others are 0. Suppose k equals to 6, we have 6 outcomes. So this vector here means that the third outcome happens. For the dice sample, it means that the dice is 3. So if you want to denote that the fifth outcome happens, the vector would be like this. The fifth component of this vector is 1, and all others are 0. The probability mass function of this distribution is defined as follows. Again, this is simply a generalization of the Bernoulli the definition of Bernoulli distribution. The parameter of the multinomial distribution is a vector mu. Mu is a vector, mu1, mu2 to mu k. And the length of this vector is k. Mu1 here means the probability that outcome 1 happens, and mu2 means similarly the probability that outcome 2 happens. And there is a constraint over this parameter. That is, the sum of its component must be 1. And the expectation of a multinomial random variable is simply the mu vector. Here, I think I need to clear two concepts. For a distribution, we have two things. The first one is random variable. And another one is a parameter. So we say x is drawn from the distribution parameterized by mu. So be careful about these two things. For example, if the distribution is multinomial, sometimes we say multinomial variable, which means x. That is the random variable this multinomial distribution is going to describe. Sometimes we call mu as multinomial parameter, which means that mu is the parameter of this multinomial distribution, and it must satisfy that the sum of the components in that vector must be 1. So when you are dealing with distribution, be careful about these two things. The third one is beta distribution. As we said before, beta distribution is mostly used as the prior of the parameter mu in Bernoulli distribution. Its density function is defined in this way. Now mu itself is a random variable, so we can define a probability density function over it. Since mu is continuous, so this probability is called density function. In this density function, we have two parameters, which is A and B. Next, we are going to discuss the meanings of these two parameters. Now let's slow down a little bit and talk about to talk about the MLE and the MAP estimation of the parameter mu in Bernoulli distribution. Remember that in MLE, the setting is like this. We have a data set which contains n samples. Each sample x is drawn from a Bernoulli distribution parameterized by mu. Now we want to estimate the value of mu from the data D. So under the maximum likelihood estimation framework, we first write down the likelihood of the data. This is the likelihood function. And here, there is a trick. Let me first write it down and explain later. Mu n1. We introduce a variable here, n1. Its meaning is the number of samples whose xi equals to 1. You can check from here to here. We start from I equals to 1 and examine its value xi. If xi equals to 1, we end it to this part. If xi equals to 0, we multiply 1 minus mu over here. So we do this from I equals to 1 to n. And finally, we get this term. Let me give you an example. Suppose we have 6, capital N equals to 6, and the value of the data is 1, 0, 1, 1, 0, 1, 0. Now we are going to go from this quantity here to here. So we go from I equals to 1 and examine its value here. X1 equals to 1. So we multiply a mu here. And the second one is 0. So this quantity here would be 1 minus mu. The third one is 1. So this quantity here in the box is mu. Similarly, the fourth one is mu, and the fifth these are all multiplied. So finally, we get mu 4, 1 minus mu 2. And look at the data set. In the 6 samples, we have 4 ones. So it is 4 here, and 2 zeros. It is 2 here. 2 equals to n minus n1. And n1 is 4 here. So any questions about this representation? Okay. What is D? D is the data set. It contains n samples.
Is U over here the same thing as U over here?
We will talk about this part later. Yeah, actually, yes. But now we are estimating this. We are talking about MLE. When we later comes to the MAP part, we will introduce this thing here.
Wait, sorry. So mu is U.
Sorry?
Mu and U are the same. They're the same variable.
You mean the mu there and here?
I'm just confused because your mu looks like a U.
Sorry, it's mu. Okay. Yeah, it should be mu. This trick here is very important. Later when we talk about the multinomials and Dirichlet, we also use this trick. So now we get the likelihood function PD given U. To estimate mu, we take the log of it. And it takes the derivative of this log likelihood with respect to mu and set it to 0. And we know that finally the estimation would be n1 over capital N. This has been illustrated in Barnabas' lecture. So this equation here is very intuitive. Remember that in Bernoulli distribution, mu means the probability that event 1, outcome 1 happens. And N1 here means from your data, how many of the samples happens by 1. So you divide the number, this number n1 over the total samples in your data set. That is the probability. Because n1 and n are both in some sense they are counts of how many times outcome 1 happens. So sometimes they are called counts. Now, given this, we are going to illustrate why A and B are called pseudo-counts. Okay.
Ideally, you should take second derivative as well, right?
Why?
Because you're maximizing the likelihood function, right?
Right, but okay, you mean that the stationary point could be the minimum, right?
Yeah.
So you need to take the second derivative to check.
Or you can simply say that the function is convex or concave. Right?
Actually, in this case, it is the max. Yeah. It is the maximum point. This is MLE estimation. In MAP estimation, what we are trying to achieve is we are going to estimate the optimal value of mu given the data set. This is posterior. According to Bayes' rule, it equals to the likelihood multiplies a prior divided over a constant. This quantity here, PD, is constant, so we can drop it and rewrite this equation into. And this guy, PD given mu, is exactly the same as we talked about in MLE. So all it matters is this quantity here. That is to say, now we are going to inspect mu as a random variable and put this prior distribution over it. So it comes to the beta distribution. So we plug in the definition of these two probabilities, and the P mu is